Both. Good morning, everyone. So it's our last Zoom meeting. This is the last teaching week also. Next week is formally the revision week. Yeah, but the 2 slots this week, we'll use them for revision. If you have any questions next week, I'm in the office. You can always knock at my door. I've had 1 or 2 emails about access to the lectures. All the Zoom lectures, the Monday slots, these have been recorded, as you should be aware, and you can access them via the Moodle page of the course. The Wednesday lectures, these have been recorded since mid-October, I think since the lecture on the 9th of October. And these ones are also accessible via the Moodle page. If you can't, please ask your classmate, because yeah, I get 1 or 2 emails every other day asking people can't access them. Most of you know it is, but it's recorded material, so it's. I'll upload after Wednesday. I'll put my scribbles also on the Moodle page. So I have 1 email query, which I'll start with. It's about the current mirror. I think in the discussions of this, I'll draw it in a more elaborate way. It's a PMOS current mirror, an NMOS current mirror. So I'll just make 1 observation about this. The current through this branch. So for a current mirror, we'll have that connection there. The current through this branch is a reference current. So I may have drawn, or a few textbooks draw this as a current source. This is not a current source. The current through here is a reference current. We can set it by choosing the value of the resistance RF. That's the simplest way of doing it. The more accurate ways of setting the reference current. But this is a reference current. It's not a current source. Yeah, 1 or 2 textbooks draw this with this symbol, IRF. I think that is incorrect way of depicting what is happening. It's just a reference current in that I out is equal to IRF. So whatever current flows in transistor Q1 is the same as in transistor Q2. So that's 1 thing I'd like to clarify. The second thing I want, the question from the email, I think in one of the discussions, one of the sessions, one of you wondered whether if this connection, if the D to S connection is not there, does it still act as a current mirror? And I think I said yes, and probably that's wrong. Not probably. I don't think it will act as a current mirror, as one of you has noted. The gate to drain connection, the diode connection, i.e. D and S connected, This makes sure that Q1 is in saturation region. So transistor Q1, if there's a current flowing, it cannot be in the linear region. It could only be in the saturation region. And this also means that Q2 will carry same current. If we don't have this diode connection, Q1 could be in the linear region. And yes, so for the current mirror to work correctly and for the current to be mirrored, for this to be done accurately, it happens when both transistors are in the saturation region or in the active region. So if this connection is not there, the two currents are not necessarily identical. So that was an email query, and I hope that clarifies. It was from one SM. I think that's the initials of the student who asked about this. Then the final question they asked is about IDS, actually related to this question. So IDS, we know it's given by half mu n Cn W over L VGS minus VTH squared 1 plus. This is not quite the form that's given in the handout, but this parameter here is called the channel modulation parameter. Ideally for an NMOS device, if that's IDS, that's VDS. For one value of VGS, ideally that's flat. But for smaller gate lengths, when we increase VDS, the current can increase a little bit, especially for short channel devices. And that is called channel modulation. We didn't discuss this in detail because yeah, we really didn't need to do that. And some of you have already done this previously, and it's something you can study on your own to fill up on what needs filling up. Yeah, so in actual transistors, especially short channel transistors, in the active region, the current will not remain flat with increasing VDS. And that's captured by this expression, or there's some variation with VDS. And we call that channel modulation. Yeah, please find out the details about that. So when we draw the small signal equivalent circuit of this is also just in answer to a question from, when we draw the small signal equivalent circuit, we'll have GM-VGS, that's VGS. And at the output, we'll have the output resistance, RDS. This is D, this is G, S, S. And RDS, in the ideal case, RDS is infinite, but it's actually an actual value because we have the current increases slightly with VDS, so we'll have an output resistance RDS. So the small signal resistance, the small signal model or the SE model or the RF model, that's the same thing. It will look like something like this. Yeah, if the frequencies are high, of course, we can include the capacitors, but for lower frequencies, we don't need to include the capacitors. So for most of the work we do on this course, Yeah, in terms of amplifiers, we're not looking at high-speed amplifiers. So GM, VGS, and RDS are adequate representation. Often RDS, we assume that the drain current is independent of VDS, so we can ignore that as well. But if we consider it, we can have a large value of RDS at that point. So that is one question from the class via email. I think the person asked is called Sitong. So Sitong, I hope you're happy. If not, please. Yeah, so Marwan, I'll go to your question once. Sitong, if you are here, can you confirm you're happy with that response to your email? No, you probably expected a response by. So the next question is from Marwan, which is for flash ADC. For flash ADC, why the top is 1.5 and the bottom? Okay, thanks, Sitong. Yeah, Marwan, that's quite easy. We can do a 2-bit flash ADC. So the best way to figure out the resistance values is to have a sketch of the transfer characteristic. If it's 2-bit, we know the outputs will be 0, 0, 0, 1, 1, 0, and 1, 1. And on the Vin divided by Vref, this is a digital output, which you can call V out. This one, we also divide it into 4 parts, and the first one is a quarter, 2/4, 3/4, and 4/4. That length is VLSB. So we want to generate, we know for the inputs in that range, and the inputs in that range, and the inputs in that range. Hope you can see that. So we'd like to generate, I can use a resistor to generate the reference voltages. So if this is my Vref, and that's my ground, remember the voltage between those two is VLSB, and between that point and that point it's VLSB. Here it's only half. So if I call my resistance there R, this one, the voltage span between those 2 points also VLSB, so that will be R. For the first position, the voltage, we only take it up to half VLSB. So that means that we need to choose this as 0.5 R, because if R gives a voltage drop of VLSB, 0.5 R will give a voltage drop of half VLSB. And for the final one, it needs to be 1.5 R, and the reason is quite simple. From this point to there, that corresponds to half VLSB, so we need R for that. But there is half VLSB that goes between that point and when the input signal is, but the input signal is never equal to Vref. The highest we go to is less by half VLSB, and therefore that's 1.5. So if I can draw it like this. So first of all, we need 4 resistors. And this is Vref. And for 0, 0, I'll explain it slightly differently because I don't. For 0, 0, any voltage is from 0 to, so the voltage drop there should be half VLSB. And in that range, the voltage drop is VLSB. And if the input signal is in that range, the output should be 0, 1. And in that range, it's VLSB also. And if the voltage is in that range, the output should be 1, 0. For the final value, this needs to be 1.5 VLSB. What's the reason for that? I'll just check in the handout to see if I have a simple explanation for that. Remember, the definition for VLSB is Vref divided by 2 to the power n. So if n is equal to 2, this is Vref divided by 4. And so this Vref divided by 4, Vref divided by 4. We split this into the 4 regions. Yeah, but the first region, because it corresponds to 0, 0, we only go halfway. The second part, we go the full VLSB. The third part, we go to the full VLSB. For the fourth part, we only need also to go a quarter VREF, but we have an extra 0.5 that would have, yeah, because we've moved everything down by half VLSB. So the other half VLSB is captured by the top resistor, but the top resistor, we really don't need, we only need half VLSB. Normally the signal is conditioned, or just the way we have an anti-aliasing filter to make sure that the highest frequencies are less than what we need. For the V-in, we can also not have V-in which is equal to Vref. So the highest V-in max will be equal to Vref minus half VLSB. Aaron, are you happy with that? So the maximum input voltage cannot be equal to Vref. Otherwise, we don't split up the amplitude properly. So we know what Vref is. We know that up to half Vref, we assign it 0, 0. And the next range, we assign it 0, 1. The next range, we assign it 1, 1. And therefore, at the top, we only need also half VLSB to assign 1, 1. Yeah, but for all these voltages to be correct, we need an extra resistance that is 0.5. So the 0.5 we took away from here, we kind of put it at the top. And we do something called signal conditioning. So before you digitize your signal, you make sure that FB is less than half FS. So you pass this through, this is what we call the anti-aliasing filter. We make sure that the frequencies, we don't have any frequency components that are higher than what we need to digitize. Yeah, because we know the signal that we are digitizing. So because of that, this signal conditioning is part of the anti-aliasing filtering that we have to do, so that higher frequency components are removed before we digitize. So similarly, the input amplitude voltage, we cannot just have any random voltages coming into our ADC. So we do also signal conditioning for that. We know what kind of amplitude voltage is coming, and the maximum input voltage will be slightly less than Vref. Of course, if it was bigger, then we'd have to choose our reference voltage differently. Hopefully that clarifies. Yeah, and Mohammed has helped me with answering that. Marwan, if you say everything adds up to VREF, and Marwan, you're happy with that. Next question. I have access to my email. If you have a question and you want just to email it now, I can check it up and we look through that. So if it's straightforward, type it in the chat or unmute and ask or email it to me. I just check my email for a second. No, any more questions? Yes, I'll probably do one question in the handout. We didn't do any of these examples. The last exercise is actually called an example. I'll do example 9. Anyway, before I do example 9, could you explain why the N for the ADC is less than 8? Yeah, the explanation is, yeah, I'll start with that, sure. Give me a second, I'll use the handout to do that. It's part of the things you're supposed to think about yourself as you go through the course. So just me saying it and you repeating it's not very useful. You need to think about it and convince yourself. You probably recognize that. You probably recognize this, sure, I hope you do. It's an R to R ladder DSC, and for this one, N is also equal or less than 8. And the reason for that, I'll do it with an example. So if the current through here is 1 milliamp into that branch, into this branch, it will be 0.5 milliamps. Because half comes this way, half goes that way. Into this, so this is for bit 1. For bit 2, the current here will be, so here it will be 0.5 or half milliamps. The current here will be a quarter. And the current here will be an eighth. 1/8 of an eighth of a milliamp. That's for bit 3. If this is bit 8, this will be 1/2 to the power 8 times a milliamp. 1/2 to the power 8 milliamps, how much is that? So how much is this in microamps? Sure, probably you can do that for me. So in microamps, 2 to the power 8 is 256, is it? Yeah. If you, so anyway, this current is very small. That means that if we have, so for this particular circuit, the current here is 0.5 milliamp. The current here in microamps, do we have an answer for that current in microamps? So that one is not. Can we have an exact number for this? So 1/256 milliamps. So it's almost 4 microamps. So here we have if we use microamps, so here we have 500 microamps flowing through for bit 1, and for bit 8 we have only 4 microamps. That's a huge difference in current, and and this current is what determines bit 8, and this one determines bit 1. And all the currents sum up at this point. So in the manufacturing of our circuit, if we have an error, if this resistor is 2.5R instead of 2R, then this can change, and maybe the current flowing through here, or if it's 1.5R instead of 2R, the current flowing through here might be the same order as the one flowing through bit 7. And so you don't have accuracy. The circuit is not very accurate. So that's why we have up to 8 bits. We can design and manufacture this circuit accurately. Beyond that, we start to struggle. So for all the Nyquist rate circuits, N is less than 8 because for the highest bit, the contribution, either the current for the resistor base types or the voltage for the capacitor base type, that contribution is quite small compared to the largest contribution. And to get this accurately, to be able to still do that accurately with N is equal to 8 or less, we can design that and it works. Beyond that, we start to struggle. So that's why it's limited to 8. And that was a question from... Sure, okay, you're happy, that's fine. Another question? Yeah, probably before we go to another question, I just wanted to go through example 9. So you probably can't read that, but you hope you have access to the handout. So example 9. I'll just summarize what the question says, and I'll give pointers on how it needs to be done. So it says that we're given a 1-bit ADC. This question is about a sigma to delta ADC, actually an oversampling ADC. Yeah, the 819 megahertz is probably wrong. The right answer I have written by my hand in the handout is like 32 megahertz. So I probably made a mistake there, Marwan. And you're given that Fs, this is the Nyquist rate sampling frequency, is 25 kilohertz. And this question is example 9. Example 9 in your handout on page 62. You're supposed to get 16. We want to achieve 16-bit resolution, or in decibels, signal to noise ratio of 96 dB. So this is the same information given in slightly different forms. So we're told the ADC should achieve a signal to noise ratio of 96 dB, or alternatively, we can give that in number of bits, that we are looking for 16-bit resolution. And we need to do this for straight oversampling. So this is without feedback. And with feedback, if it's with feedback, then we are talking about a sigma to delta ADC. So to be able to answer this question, so the question asks, us to find Fs prime. That's what the question asks us to do. Fs is the oversampling frequency. Fs prime we know is equal to k times Fs, where k is the oversampling ratio, and k we normally write it as 2m times Fs. So we are given that. So for straight oversampling, I'll just write the equation from the handout. For straight oversampling, the signal to noise ratio SNR in decibels is equation 109 in your handout, which is 6.02 n plus 0.5 m plus 1.76 dB. That is the signal to noise ratio for straight oversampling. Or I could write it here also, SNR for straight oversampling was equal to 0.5 root 1.5. And this one, if we convert it into decibels, it gives us that expression. While for the sigma to delta ADC, we didn't derive this in class, but we know in theory how to do that. The signal to noise ratio is given by equation 131, and SNR dB is equal to 6.02 n plus 1.5 m minus 3.41 decibels. That's equation 131 in your handout. And we could also have an expression similar to this. So to answer this question, remember we defined effective number of bits, and this is equal to n plus 0.5 m for this particular case. N is given as 1. So if we find m, then we put m there. We know that's 25. Then we know our expression for Fs. So for the first part, we can use this equation. This is equal to SNR in decibels minus 1.76 divided by 6.02. Yeah, I'm probably just overdoing this a little bit, but if I probably don't need to carry on here. So we're looking for 16-bit resolution. We know that n is equal to 1, and therefore m would have to be equal to 10. And so you can put 2 to the power 10 times Fs. You'll find the answer for straight oversampling. And the effective number of bits for the sigma to delta is equal to n plus 1.5 m. So the first one, m is equal to 30. So n is equal to 16. Effective number of bits is equal to 16. N is equal to 1. Yeah, so m will be equal to, yeah, more than you, right? So we have 16 is equal to 1 plus 0.5 m. So m will be equal to 15 times 2, which is equal to 30. And then you stick that number into this expression, multiply by 25 kilohertz, and you get a large frequency. For the sigma to delta, we use exactly the similar expression, n or b. That were 2 ways of doing it. For the sigma to delta, the n effective number of bits is 1.5 m. So that is 16. That is 16. This one is 1. We get the value of m. We put it there. And yeah, I think if I do it that way, I probably get 819. But if I do it using dB, I get probably around 30 megahertz. Yeah, whatever. I think the way you do it is what counts in this particular case. Marwan, you had some. I mean, you've already gone through this. Do you need me to say anything more, or you're happy with this explanation? So you can use effective number of bits, you'll get an answer. We are told this should be 16-bit resolution, so that is 16. We are told n is equal to 1, so it's trivial to find m. Once we find m, we stick it in there, and we find the oversampling frequency. But we can also do this, solve this question by using decibels. We are told that the resolution should be 96 dB. So we're told that that number should be 96. We know this is the effective number of bits. This is equal to 1. You put this in this equation, you find the m, you put it in there, and you find the oversampling ratio. And the two answers might be a little bit different from when you use decibels and when you use just the 16 bits and use this, what we know to be the effective number of bits. But yeah, that's it's that difference is a little bit cosmetic. It's just because we are not thorough in the analysis. But both approaches give us the value that we need in terms of oversampling. So I think that's as much as I want to say about example 9. Bottom line is the two ways you can do this, and both of them are okay. Either use 16-bit resolution or use 96, use the decibel expression, and whatever numbers come out of the your calculations, that would be fine. So next question, another question that we want to go through. If you've emailed, I'm not my email is on a different computer, so I'll just check the different computer in case one of you has. If you email, ask me to check the email because I'll need to look at it on a different computer. So any more questions or comments or any parts of the course we need to, yeah, anything more that I need to answer? Yeah, probably not. We can have an early break. For Wednesday, please do email because the lecture theater is pretty huge. So if you have questions, please email them to me beforehand on Wednesday. Then I'll just go through the email questions. And of course, if you have a spontaneous question, you can always come to the front and ask or write it on paper and pass it on. Okay, if there's not anything more, I think I'll hang around until 10 minutes to the hour. So I'm around. If there's any question, just pop it up in the chat and I'll respond. Otherwise, those of you who want to take off, that's okay. You can have an early break. We'll see you on Wednesday. But I'm around for anyone with any question that pops up until 10 to the hour. Yes, someone a question by email that the get current. I'll do that, Jeffan. I'll do the lecture script. I'll upload the lecture scribbles after Wednesday on Wednesday, on Thursday morning, to be precise. So after the last meeting on Wednesday. So one of you is asking, so Siton. That's the structure of your MOSFET, Siton, and the gate sits there. So the current, the DC current is 0. So we don't have any DC current flowing through the gate. So yeah, of course, we can have AC current because this is a capacitor. AC current goes through a capacitor, so that can happen, but we don't have any DC current going through the gate. But you need the gate to be able to, it's called a gate because it's the control signal to either turn this transistor on or off. At the exam, Mohammed, look at past questions. So there's a mixture. There is a mixture of the exam asks you to show an understanding and also to comment on where a topology may be used. Yeah, they're not just theoretical questions, and you need to have an understanding of how the various components we've discussed work. So Siton, the best way is to look at past papers. You'll see how they look like. So Siton, I don't understand your question, but we can't. The gate is important. We cannot just because no current goes through it. It doesn't mean it's not doing something. It's doing something because it sets the current through the N and the S. Without the gate voltage, we don't have control of what happens between those two, between the two main electrodes. So I probably misunderstand your question, but if I do, you can rephrase it. Yeah, so the gate into the current into the DC current into the MOSFET is 0. So it draws no DC current. That's one of the positives. But that's why it's also called a field effect transistor. MOSFET, field effect transistor. So that name comes from the fact that it actually doesn't take any DC current, just the electric field from the gate. Even though no DC current flows, we are able to control the DC current between drain and the source. So it's the DC current is 0. That's partly the reason why the transistor has this name, field effect transistor. So it's called a FET, and then we add the MOS. This part here just says what the gate is doing. So the gate is connected to the metal, and there's an oxide between it, and then the semiconductor. Then we have the transistor. So we have the MOSFET. Any other final question or comment from anybody? No. Should we use a question? So Kun, for a question, example 9. Example 9. Spread over sampling. Use En or B is equal to N plus 0.5 M. ADC, use En or B is equal to N plus 1.5 M. Is that any clear? Kunle. So the exam, there'll be 3 questions for each section. So section A, which is the digital part, will have 3 questions and you should answer 2. For section B, which is the analog part, it will also have 3 questions and you should answer 2 out of the 3. So you answer two out of 3 questions for each section. So a total of 4 questions, and yeah. It's not the same as last year. Last year, there were only 4 questions because it was online, so we reduced the number of questions. And you had to answer all the questions. This year, you have a choice. You have more questions. You have 3 questions, and you answer 2 out of the 3. So like in previously, yes, last year we changed a little bit because it was online. Yeah, it's 10 to the hour, so we'll see you guys on Wednesday. Please try and email in questions so that it's easier to deal with them at the Wednesday class. So see you on Wednesday. Bye then.